Hello everyone, welcome to the basic concepts of network theory or circuit theory part 2. Okay, so in the last class we discussed about some of the basic terminologies and we stopped at the identification of nodes, branches and loops in the circuit. So let us continue with our next concept, and that is network versus the circuit. First, let us need to understand, because we use the term interchangeably as network theory and sometimes circuit theory. So we need to understand what is the difference between network and a circuit. So let me draw one simple, I would say, figure A and another figure B. So the resistances are R1 and R2. I will name this as figure B. So if you see the difference between figure A and figure B, the figure A is basically a network and figure B is a circuit. So looking at these figures, I hope it is very much clear. Circuit is the one which has a closed path for the flow of current. Network may not provide a closed path. So you can see the circuit terminals are open circuited in the case of the network, while in the circuit you have a closed path. So this is a very important thing because we use the term interchangeably as sometimes networks and sometimes circuits. So this is the difference. One provides a closed path, one may not provide a closed path. So an electrical circuit can always include one or more networks forming closed paths. So this is an important concept to be remembered. Moving on to the next one, we have to identify the various sources. So let us look at the classification of sources. Mainly, the sources are classified into two main categories, that is the voltage source and the current source. Now together these can be further classified as independent and dependent sources. So we can have a voltage source that is dependent and independent. We can have current sources which are independent and dependent. So let us look at the first classification, independent sources. So under this, the independent sources are generally represented by a circle. And if it is going to be a voltage source, we will specify the polarity. So if it is going to be a DC voltage source, we will have positive, negative specified. And for an AC source, we will be having a sinusoidal symbol within the round shape. So this is a AC voltage source, which I am representing as VA. So these both are voltage sources. So when it comes to the current sources, we will specify the independent current sources using a round shape similar to the voltage sources, but here the arrow mark is going to be specified. So this is a current source. Now coming to the dependent sources, the dependent sources will be represented with a diamond shape, right? So again we can have dependent voltage sources and dependent current sources. So let me write the classification again. Let us first look at the dependent current sources. So the dependent current sources are further classified as well as the voltage sources are also further classified. So kindly observe the way the representations are. Voltage sources will have polarity, whereas current sources will have the indication of the direction of current. Current sources can be further classified as current controlled current source, which is I corresponding to current, and we can have voltage controlled current source. Now since they are dependent sources, they are dependent on some parameter. So in the first case here we have the dependence on the current which is flowing in some part of the circuit. So Ix could be flowing in some part of the circuit. So this is current controlled current source. Similarly, we can have voltage controlled current source, which means Vx is some value of voltage which is present across some element in the circuit. Again, in voltage sources we can have classification such as current controlled voltage source and voltage controlled voltage source. Current controlled means it is dependent on some value of current, but it's a voltage source. So it is say 3 times Ix in a similar manner like the previous, dependent on some value of current. And here voltage controlled voltage source means it is dependent on some value of voltage. Now another important aspect which is very important is rise and fall in potential. So generally we do not understand what is the meaning of voltage drop and voltage rise. For this, let me consider a resistor with the current I that is flowing across this, and if I am considering the conventional current direction, this is the polarity I will assign for my resistor, positive and negative. So this is equivalent to me drawing a voltage source across the resistance, that is V plus minus, and this is my current direction. So since as my current moves, it is changing from positive to negative, I can say this is voltage drop. Now say I have the same resistor with the direction of current in a similar fashion, but I am considering my conventional current direction to be opposite. Now what happens is that the polarity of the across the resistor will change. It's going to be minus plus. So in such a case, you are moving in the opposite direction to the current, and this is considered as voltage rise. So generally when we do circuit analysis, it is the voltage drop that we consider from positive to negative. So it is very important to remember these things, because it becomes a tandem task, especially when you are writing KVL equations. If you write the wrong polarity, your answers will be incorrect. So remember that we always go with the voltage drop concept by default. There's nothing wrong in the opposite also, but sometimes it can be quite confusing. So better we prefer the voltage drop. Now next, let us look at the series and parallel circuit. So first we will look at the series circuit. So in a series circuit, we always consider the current that is flowing to be the same, because you have only one single closed path, right? Before that, let me just tell you what is the meaning of connection in series. So basically when we say the elements are connected in series, means they are connected just at one single point. So this is one point connection that you have between these two elements. So if I consider this to be say R1 and R2, R1 and R2 are connected only at one particular point. So here the current that is flowing is the same. The current that flows across R1 is the same current that flows across R2. So if I say current I, it is the same current that flows across R1 and R2. Now let me consider the drop across the resistor R1 as V1 and the drop across resistor R2 as say V2. Now here in the series circuit, the drops across the resistors would be different. It is not the same voltage that is present, but if the resistances are equal in value, then we can have the same drop V1 and V2. But in a series circuit, in general case, we have the source voltage to be equal to the sum of the voltage drops in the individual circuit element. So I can write Vs is equal to V1 plus V2. And the current, if I say across R1 is I1 and current across say R2 is I2, then I can say I1 is equal to I2 is equal to I. Now resistances in series are generally added, so you can say the total equivalent resistance will be equal to R1 plus R2. Now let us look at the parallel circuit. Let me consider a simple parallel circuit with two resistances R1 and R2 again. Now before that, we say the two resistances are connected in parallel if they are connected at both the points. Okay, so we have resistance R1 and R2 connected at both the points. That is shown here. This would be the first point of connection. Another point is this point. They are connected end to end and have common points. Two common points are present. So that is when we say it is in parallel. Now in a parallel circuit, we have the voltage drops across the parallel circuit to be the same. So say I consider this is node 1 and this is node 2. The resistances R1 and R2 are connected at both the ends. So say I mark the current across R1 as I1 and other current as I2. The source current is I. The current is actually getting divided between the two resistors R1 and R2. So the currents in the parallel circuit will be different, whereas the voltages are going to be the same. Let me mark the voltages as V1 and V2. So here the voltages are the same. So Vs will be equal to V1 equal to V2, whereas the currents Is will be equal to I1 plus I2. Now if you want to compute the equivalent resistance of this parallel circuit, you have to use the equation 1 by R total is equal to 1 by R1 plus 1 by R2. Since only two resistances are present, I can directly mention it as R total to be equal to cross multiply, and you get R1 R2 divided by R1 plus R2. Now this works well if you are having only two resistances, but otherwise you have to compute the reciprocal and then take the inverse to compute the R total. Okay, so if you have understood that, I will give you one simple parallel and series connection. Let's see if we can identify whether what the value of equivalent current and voltage sources would be. So if you see in this particular circuit, the I total will be equal to I1, because it's entering, current I1 is entering while current I2 is leaving, so it's minus I2 plus I3. So when I say the current is getting divided, we have to be very careful as to how, because the polarity also matters. Whether the current is getting added or subtracted, you have to see. Similarly, if I consider another circuit with voltages in series and I am asked to compute say voltage between the terminals. So here VAB will be equal to, you have to be very careful with the polarity, it is going to be equal to V1 plus V1 plus V2 minus V3, since the polarity of V3 is negative.